Hello friends, in this class we will see the representation of signed arithmetic numbers. Generally, we will represent a normal number in terms of positive and negative number. We didn't see till now. Now we will see the signed representations. Generally, there are three signed representations. One is magnitude. Second one is one's complement. And third one is signed two's complement number. Now we will see the representation of numbers using sign magnitude. This is sign binary representation. First we will see the magnitude representation. This is signed magnitude representation. Let us take value. This is the decimal value, and this binary equivalent is 0, 1, 1. Okay, this is 3. First, see the binary value of 3 is 0, 1, 1. In signed magnitude representation for positive numbers, we will take signed bit as 0. For negative numbers, we will take signed bit as 1. Here this signed bit as 0 or 1, this will be in MSB. Let's see an example. This is 5 base 10. This 5 is equivalent to this 4 to 1. This is 1, 0, 1 base 2. For plus 5, first of all we will write the binary equivalent of 5, 1, 0, 1. For plus, we will take the signed bit as 0 in magnitude representation. So this is for plus 5. For minus 5, we will take the value of 5 as 101. For minus, we are using the bit as 1. This is for the signed magnitude representation. And we will see for 0. Here in 0, we can take two types. If we take the plus 0, we will get one value. For minus 0, we will get another value. But we know that 0 is neither positive number nor negative number. So this is the drawback in signed magnitude representation. We will overcome it in next representations. First we will see the value of 0 is nothing but I am representing in terms of 3 bits. 0, 0, 0. Here this is the signed bit, this is the signed bit. Here the signed bit is for plus 0, for minus 0, this is 0, 0, this is for signed bit. This is also for signed bit. This is the major drawback in signed magnitude representation. Because for 0 there are two representations, but according to us 0 is neither positive nor negative, so definitely we should get only one representation. This will be overcome in next representations. So I am taking 2 bits. For 2 bits we will get the 4 levels. This is 2, 1. For 0, I am taking it as 0, 0. For plus, this is for plus 0 or minus 0. Plus 1, plus 2, plus 3. For 2 bits, the maximum value is plus 3. Because for 2 bits, we will get the 4 values. The maximum value will be when these 2 bits are 1s. That means sum is 3. So the maximum value here is 3. First of all, I am writing the values of normal representations. For 0, the binary value is 0, 0. For 1, 0, 1. For 2, 1, 0. For 3, 1, 1. 2, 4, 0 and 2, 4, 1 value. For minus 0, first we will write the value for zeros. This for 1, 0, 1, 2, 1, 0. For plus, for positive numbers, we are giving the MSB bit as 0. Here for negative, we are giving it as 1. This is the final values. Here, the total values here are 1, 2, 3, 4, 5, 6, 7, 8. At the total, there are 8. That means for 2 bits, we are getting it as 8. We can generalize that it as range of n bit sign magnitude representation equal to minus 2 power n minus 1 minus 1 to 2 power n minus 1 minus 1. These for minus values, for these for plus values. These for 2 bits. For n equal to, here for 2 bits we are taking this, but including the side bit we are getting as total 3 bits. So n equal to 3 equal to minus, I am writing here, equal to minus 2 power 3 minus 1 minus 1 to 2 power 3 minus 1 minus 1. This is equal to this minus of this is 2 power 3 minus 1 is nothing but 2 square 4. 4 minus 1 is 3. 2 square is 4. 4 minus 1 is 3. This is minus 3 to plus 3. Say minus 3 to plus 3. This is the range of the values for n bit sided magnitude representation. Now we'll see the sign one's complement representation. Here in one sign, one's complement representation, the roots are for positive number, this for negative number. Let us take an example of plus 3. Plus 3 means, first of all, for 3 we will write the binary value. This is 1, 1. Plus is nothing but 0. For negative number, we will take the 1's complement of plus 3. That means minus 3 equal to 1's complement of plus 3, which is equal to, take the complement. Complement is nothing but bit 1 is inverted to 0 and 0 is inverted to 1. This is 0, 0, 1. And this is for minus 3, 1, 0, 0. Here's an example. Find 1's complement of plus 9 and minus 9 base 10. So first, for plus 9 to the base 10, first we will write the binary number of 9. Binary number of 9 is nothing but here 1, 0, 0, 1. 8 plus 1 is 9. This 1, 0, 0, 1. Plus indicates the signed bit. This is 0. For minus 9, we will take the minus 9 to the base 10 equal to here. This is 1's complement representation. 1's complement of plus 9 is different from 1's complement representation of plus 9. The 1's minus 9 to the base 10 equal to 1's complement of plus 9 to the base 10 equal to complement of this is nothing but this is 0, 1, 1, 0 and this is 1. So this indicates that the number is negative. Here for 0, take 0 as plus 0 and minus 0. Later we will see that plus 0 and minus 0 are same or different. First for 0, I am writing in terms of 3 bits. See, for 0 binary value is 000, plus is nothing but 0. Minus 0 is nothing but 1's complement of here. 1's complement representation of minus 0 to the base 10 equal to 1's complement of plus 0 to the base 10. Here this is base 10. 1's complement of plus 10. This is plus 10 values. 1's complement is nothing but here all are 1's. Here we are getting the values for plus 0 and minus 0 as different. So in 1's complement also there is a drawback. The drawback is 0 has two different values in binary. This is the drawback in 1's complement representation. Now we will see the third representation, sign 2's complement representation. Let us take an example of plus 7 base 10. Here plus 7 is nothing but a positive number. For 7 the binary value is 111. Plus indicates that the number is positive number. For positive number the bit will be MSB bit will be 0, signed bit. Now this is for minus 10 to the minus 7 to the base 10. We will represent by using sign 2's complement. This is 2's complement representation. How to represent minus 7 to the base 10 in 2's complement form? This is equal to 2's complement of plus 7 to the base 10. While attempting any questions in the exam, we need to first of all you differentiate between the complement representation and complement of. Two's complement of, let's take x is a decimal value, minus x, two's complement representation. This is also known as form. Two's complement form or representation of a negative number minus x to the base 10 equal to 2's complement of plus x to the base 10. This is very important, otherwise we will get confused. So for minus 7 base 10, the 2's complement representation is 2's complement of plus 7 to the base 10. Take the 2's complement. For finding the 2's complement, first find the 1's complement. Here 1's complement of this is nothing but 0, 0, 0, 1. For 2's complement, this is 1's complement. 2's complement equal to, add plus 1 to this, we will get the 2's complement. This 1, 0, 0, 1. Here 1 indicates that the number is negative. Let us take another example of minus 9. Find two's complement and 2's complement representation of plus 8 to the base 10 and for positive number 2's complement representation or 1's complement representation is nothing but the normal representation. For positive number, just find the binary equivalent value of 8 and for plus just add the bit as sign bit as 0. That is the 2's complement representation or 1's complement representation. But for minus 8, so nothing but for plus 8 in 2's complement form or representation equal to, for 8 the value is 1, 0, 0. For 0 sign bit, 2's complement representation of minus 8 to the base 10 equal to 2's complement of plus 8 to the base 10. For plus 8 to the base 10, 2's complement is nothing but 1's complement plus 1. First find the 1's complement. For this 1's complement is nothing but 1, 1, 1, 0, 1. 2's complement equal to, just add 1, 1 plus 1, 0. Here this 1 plus 1, 0. We will get as 1 carry, 1 plus 1, 0. Carry will be 1, 1, 1. This is the 2's complement of plus 8 to the base 10, which is nothing but 2's complement representation of minus 8 to the base 10 equal to this value, equal to 1, 1. This 1 represents that number is negative. Instead of always taking the 1's complement and adding the 1, we can do it directly. First find the plus 8 to the base 10 2's complement value. For plus 8 to the base 10, this is the equivalent value. Let us take an example of 1 0 1 1 0. 2's complement is nothing but write the 0 as it is 0, 1 as it is right. Whenever we get the bit 1, before the bit 1, just complement all the values. 1 is 0, 0 as 1, 1 as 0. This is direct 2's complement representation. For 0, 1, 3 equals 0, we can write directly. Whenever we get zeros, just write the zeros. Whenever we get 1, simply write the same 1. Before the values of 1, just complement all the values. Complement of 0 is 1. This is the 2's complement value. It's nothing but 1 1 0 0. In the previous representations of sign and magnitude and one's magnitude representations, we have got two drawbacks. The drawback in sign magnitude representation is 0 has two extents, two values. In one's complement also 0 had two values. But in sign 2's complement representation, we didn't have two values. We have only one value. This is the major advantage of 2's complement representation. Plus 0 to the base 10 equal to, for 0 is nothing but 000. Plus is nothing but this value. For minus 0 to the base 10, this is 2's complement representation of plus 0. This is 2's complement representation of equal to, this we can write it as, this is 2's complement of plus 0 to the base 10. The value of plus 0 to the base 10 is this. 2's complement is nothing but whenever this is 0 0 0 0, this is the 2's complement form. Otherwise, just this is all zeros. 2's complement of plus 10 to the base 10 is nothing but 1's complement of plus 0 to the base 10 plus 1 is the 2's complement. This is the 1's, this is the 1 for 1's complement of plus 10 is nothing but all 1's. 2's complement is nothing but just we'll add a 1. 1 plus 1 0, carry is 1 plus 1 is 0, carry is 1 plus 1 is 0, carry is 1 plus 1 is 0, carry is 1. Here we are getting all zeros. This is the advantage in 2's complement representation. So we have only one value for 0.